So hello everyone, welcome to another talk in our Colloquium series. So it is my pleasure to introduce Dr. Caroline Lemieux from the School of Computer Science at University of British Columbia. Dr. Lemieux's research focuses on building tools for improving correctness, security, and performance of software systems. Her research received distinguished award from ACM software conferences, and she received the Bachelor of Science, Computer Science from University of British Columbia, where she won Governor General Silver Medal. She received a PhD from University of California, Berkeley, where and also received Berkeley grad fellowship and also Google PhD fellowships, and she was also a postdoctoral fellow at Microsoft. And today, Dr. Lemieux gives a talk for us about challenges in software testing. Is that correct?
Yeah.
Perfect. The floor is yours, please.
All right. Thank you so much for that kind introduction. So the kind of foundational issue that guides a lot of my research is the fact that modern software still has bugs. And as that software becomes increasingly pervasive throughout different aspects of our lives, those bugs can have increasingly severe consequences. Right. For instance, in the last few years, we've seen a number of pretty bad security vulnerabilities emerge from just basic correctness bugs in C and C++ programs. And not all bugs get to the stage where they get a logo and news stories written about them, but we know they're quite costly on the back end. This report from back in 2018 put the cost of poor quality software in the United States alone at nearly $2.8 trillion. So if we extrapolate that to the world in 2023, we can see that these costs get quite extensive. So the goal in my research, as was introduced, is to build tools that help developers improve the correctness, security, and performance of software to help contend with some of the costs of poor quality software. Now, my work in programming languages and software engineering kind of revolves around three main areas of specification mining, program synthesis, and automated testing. And my works over the years have touched the different intersections of these areas with a particular focus on automated testing. And in particular, in some of my more recent works, I've looked at the intersection of automated testing and machine learning through the RLCheck work in 2020 and the Codex work. And today I'm really going to focus on that particular intersection and talk a bit about, the good and the bad that we got when we tried to bring machine learning to help automated software testing. So first, I'll talk about the RLCheck work, where we use reinforcement learning to improve automated test input generation. And I'll also spend some time talking about the Codex work, which is a lot more timely in its technologies, where we tried to use large language models, kind of like ChatGPT, to improve automated test suite generation. Now, I'm going to define all those terms as we get to them, but the essential way I'm going to structure this talk is give you a bit of background about both techniques, then give you a sense of the core approaches, and maybe some evaluation and challenges of each approach. And I hope that will leave you with, enough information that if it piques your interest, you'll have we can have a little discussion and some questions at the end. So I'll get started with all this by giving you some background into the RLCheck work, and in particular, some background into automated testing more broadly. So typically the way that humans write tests, you're supposed to sit down and think carefully about your test cases. And hopefully that will ensure that no bugs make it into your programs. But humans are not infallible. And back in 1990, there was this Communications, the ACM article that coined the term fuzz testing. And what they did is they found that if you took a bunch of popular Unix utilities, so command line programs, and you sent to them just random sequences of characters as input, eventually some of those sequences of random garbage characters would cause the programs to crash. And they called their tool, which created that random input, Fuzz tool, And this birthed the term fuzz testing, which I'll use throughout the first half of my talk. And it's become a tool that's really popular, both in industry and academia, to automatically find bugs in software. Now, pure fuzz testing is this. It's just sending random sequences of characters to a program under test. But since the 1990s, things have gotten a little more complex. And if you find yourself wanting to fuzz something more complex than like a command line utility that processes raw characters, say you want to randomly test a compiler, like here, the Google Closure compiler. If you just send it random garbage sequences of characters, regardless of your feelings towards JavaScript, this JavaScript compiler will figure out pretty quickly that random sequences of characters doesn't look like JavaScript, and it will immediately exit. And this means that with this like pure random testing, you may be able to find bugs in those early validation stages of the compiler, but you won't be able to find bugs much deeper in the program under test. So one of the things you can do instead of doing pure random fuzzing is doing generator-based fuzzing. And essentially, this is also called in the functional programming community property-based testing. And essentially the idea there is to, instead of having a source of randomness, you have this input generator, which is usually a handwritten program that each time you call, it's a non-deterministic function that each time you call it returns a random input, but in a given search space, right? So I might handwrite an input generator for JavaScript, and when I call it, it'll give me a bunch of different, little JavaScript programs, which even though they might look a little random, they might not be very, very complex, but when you send them to this compiler, it will actually recognize, hey, that kind of looks like what I expect, and it'll do stuff. It might actually get into some of the compilation stages of the program, and you might be actually exercising some interesting behaviors of your compiler and actually able to test them. So this is actually a very powerful technique on its own. If you can get the input generator to match the space of inputs that your program under test expects. But as you might expect, this is not always that simple. And I'm going to give you an in-depth example of this, but I'm going to use a much simpler test program just for ease of explanation. So let's go back to the basics and say that the program we want to test is a program which takes in binary trees. Now, the nice thing about generating binary trees is that I can show you a simple generator for binary trees on one slide. So how this works, this is kind of written in some pseudo Python. How this works is you start executing it, you get to this place where you make a random choice for the value at the root of the tree. And for instance, you might choose randomly the value 2. Then you randomly choose whether or not to generate a left child for the tree. Say yes. Then you'll recursively call this function and generate a whole other binary tree rooted at the left node, where you'll again have to choose a value for the left-hand side. So that's kind of what a binary tree generator may look like. Now, the types of programs that you can test with so what kind of test program might we be looking into? Here's a simple program that we might want to test that takes in binary trees. So this program takes in, I've written some notation here that says this tree parameter should be generated by our binary tree generator, and then this toAdd parameter should be generated by some int generator. And essentially what this test does is first it checks whether the tree we gave it is a binary search tree. So unlike regular binary trees, binary search trees have an ordering property, which I'll put up a bit later on. So what this really is testing is that binary search tree insertion property. And first it's checking, was the tree that you gave me a binary search tree? If it is, try to insert a new integer in the binary search tree and assert that the tree is still a binary search tree, right? And if we test this with enough, random looking binary search trees and enough random integers, we'll probably have a good sense as to whether our implementation is correct. Or at least it preserves the binary search tree property. So the nice thing about this test is that this assumption statement, it returns true. It returns just early if the tree that you've given it is not a binary search tree. So what this allows you to do essentially is rejection sampling. So we wrote a really simple binary tree generator. It's one that you could probably come up with in like 5 minutes. And now we can use it to test a more complex program, one that actually, expects inputs that have some constraints on them, like being a binary search tree. So that's nice. But there's a little catch here, which is that, if I'm testing this with 1,000 inputs and only 13 of them ended up actually passing this assumption statement, suddenly my random testing looks a lot less effective because I haven't actually tested the binary search tree input, the binary search tree property on 1,000 inputs. I've only tested on 13 because all the other ones failed out at this assumption statement. So one of the core problems we see here is, how many rejections might we get? And to give you a sense of what a problem this is, even for this simple example, just consider the probability of generating a binary search tree from this generator, right? If we're again at the point where we've chosen to generate a tree with value 2 as the root node, and then we choose to generate a left child for it. When we get to generating the value for that left child, there's actually only 2 values. If you remember the binary search tree property, amongst other things, the left value needs to be smaller than the parent. So there's only 2 values that could possibly give you a valid binary search tree from this point. And from this point, actually, if you do a bit of math, the probability of generating a valid binary search tree of size 2 here is only about 9%. And the probability of generating a valid one of size 3 is only about 2%. And as you get larger, you can see these probabilities of generating valid binary search trees of larger size is going to get smaller and smaller. So we kind of have a trade-off here, right? So either we could use this easy, untuned generator, just generates, binary trees that might not have the right property, but then we can use it for testing all other types of, programs that take in some sort of type of binary tree. But unfortunately, as we saw, the probability of generating valid trees for checking, for testing might be quite low. So, we might say only get 13 out of 1,000 tests that are valid, interesting binary search trees, and our random testing is going to be quite ineffective. So now, on the other hand, we could spend some time, and tune this generator over here so that, it actually keeps track of the ranges for values depending on where you are in your generation process. And that doesn't seem too ridiculous to do in this case. And, it would give us, 1,000, all of our tests would be valid binary search trees if we just put in that extra effort. But if you think about this more broadly, when you're getting to data structures that are more complex than just a binary search tree, it might actually become quite tedious to retune that generator for different, assumptions that you have in your different tests. And it's not really going to be a tool that developers will want to use. So the goal of using machine learning here was to see whether we could auto-tune these generators and essentially get an easy to write and reuse generator, but one that would give us effective checking and mostly generate valid inputs. So that brings me to the core approach of RLCheck. So, okay, I've had this piece of code up here for a while, right? Remember, our problem is that we want to generate a binary search tree. And what you can notice is that this generator is actually capable of generating binary search trees, right? There are some sequences of decisions through this generator that will create valid binary search trees. Is just as we saw previously, they occur with low probability. So one thing we asked here is, well, could we make those occur with higher probability by, instead of taking these choices of, random values and whether or not to generate a left or right child, instead of taking these choices randomly, could we make those choices according to some distribution where, the value we return at each point is a value that maximizes the chance of generating a valid input. The difficulty there is that there's not one right answer for each of these choice points. The right answer kind of depends on context. What I mean by that, right, is as we've seen, right, if you're the left child of the two, there's a certain set of choices that are good. If you're the right child of the two, there's another set of choices that are good, right? Everything from 3 upwards. And again, if you're the left child of the 7, which is the right child of the 2, there's another set of choices that are good. So really what we want to do is that we want this randomness to not just return a uniform random choice. We want it to return the ith, like an ith choice with a probability that's conditioned on the context, where the probability of the choice in that context is higher if that choice is good in that context. And this problem of encoding, this rough notion of context that we have here, which is kind of the generation state, it's kind of a hard problem. So what we did in the RLCheck paper is we came up with a heuristic, which is essentially that if you think of the state of generation so far, that's kind of like the sequence of choices that have led to the current generation stage. So I'll show you an example, but you can track that quite easily by just, adding a context parameter that just keeps track of all the choices, the random choices you've made so far. So for instance, when we're the left child of the 2, our context will be the list 2 and left. So after we have this context, then, we can do what we want, which is we can add that context as an additional parameter and hopefully find some way to condition those choices on those contexts. And if we zoom in, what we have at this point is that we have a choice space, like here, the value we want to put in that binary search tree. And we want to take the best choice given a certain context, which is the sequence of actions taken so far. And I realized that this kind of sounded like the problem solved by reinforcement learning, right? Where we want to take the best choice given the current context, and reinforcement learning tries to essentially take the best action given the current state. So the idea in RLCheck is to replace all these random choices with some essentially guides for choices, which are actually in the form of a reinforcement learning agent, which is learning kind of a new probability distribution for choices as we go along in the testing process. And the RL we used actually is quite simple. The state we're taking is just the last k elements of context. The actions we're taking is just the choice space at each point. We have this funky reward structure where we give a low reward for invalid inputs and a high reward for new valid inputs. And essentially, if you're not familiar with Q-learning, in like table-based Q-learning, the way it works is that you just have a table that stores for each state and action pair the mean rewards you've seen so far for that state and action pair. So in our case, like choice and context. And then essentially what we do is we have an epsilon greedy policy, which takes the action with the highest score in this Q table, so the highest mean rewards seen so far, except with probability epsilon, where we take a random choice. And we actually used an unusually high epsilon for this testing case. But zooming back at a high level, what we've done in RLCheck is taken this generator-based fuzzing, and instead of just having this generator, generate pure random inputs, we add in a loop where we get some execution feedback from the program, and then use that execution feedback to essentially guide the next generations of the generator. And in particular, we get from the program whether the input we just generated is valid, and we can see whether it's unique just syntactically. And then these RL agents use that information to guide the generator to generate more valid inputs. So that's kind of the core thing we do. So the next question is, did this work? And it did to some extent it did. So if we measure just the first problem I was talking about, which is essentially the problem of not being able to generate enough unique valid inputs. What this graph shows, the green line is our RLCheck approach, the time is on the x-axis, and the number of unique valid inputs generated is on the y-axis. And you can see that our approach generates far more unique valid inputs than our two baselines, which were random and another kind of fuzzing baseline. And this is sort of the closure compiler I talked about at the beginning of the motivation. So generating unique JavaScript programs. And what we see is that for all the benchmarks, for nearly all the benchmarks, except that benchmark C, which I'll get back to, we were actually able to generate orders of magnitude more unique valid inputs. And when we translate this to bug discovery ability, so it's a big table, but we're going to zoom into different parts of it. So on two of the benchmarks where we had that big gap and that RLCheck was able to generate many more unique valid inputs, what this table shows is for each bug, the average time to find it, and then the percent of the 10 runs on which that bug was found. And we see that in general, RLCheck is kind of able to get the best of both this random baseline and this other coverage guided baseline. And it's able to find those bugs faster and somewhat more reliably than the random approach. However, on that one benchmark I pointed out, where you see the green line is somewhat above that blue dash dotted line, but the blue dash dotted line just means random generation. So actually random is doing a good job of generating unique valid inputs on its own. On that benchmark where, there's not so much this problem of generating valid inputs with the random generator, it looks like RLCheck might be overfitting to a certain part of the valid input space because it actually had slightly lesser bug discovery capabilities than the pure random approach. So just quickly, you might ask, why were you just using, table-based reinforcement learning? What if you use deep reinforcement learning? And I actually had an undergrad study this as well. And he essentially used this deep Q learning approach, which I'll just highlight the differences. The core difference is that table is replaced with a 2-layer neural net, and we have this cool extra reward based on curiosity, which comes from a reward that was used to play games. But we still have unusually high sampling, this unusually high random sampling. And what we found, we found some good of that deep learning approach. So on the x-axis here is the size of valid inputs, and on the y-axis is the number of unique valid inputs of that size that were generated. The green line here, this is a regular RLCheck I've been talking to you. And we see that most of the valid inputs it generates for this particular benchmark were mostly like size 10 is really the mode of the distribution here. While the deep net approach has a distribution that seems to be able to generate much more valid inputs of larger size. So it seems like it's maybe not overfitting as much to like a very small part of the valid input space. But on the other hand, here's a table. It shows different methods on this benchmark. And if you look at the number of unique valid inputs generated versus out of the total, look, it looks great for the deep learning. It definitely generates more unique valid inputs. But if you look at the time it takes, it's actually a huge slowdown. So while random testing took 5 seconds to generate 50,000 inputs, our deep learning approaches took, thousands of seconds. So in the end, there's still a problem here in terms of if we're going to add something heavy duty like deep learning, it really needs to be that the trade-off what we're getting from it is worth this potential slowdown. All right. So that kind of ends my little chat about RLCheck. So is a really promising approach in that it seems like RL might be well suited to this problem and generates more valid inputs. But if you find yourself, seeing this state action abstraction and thinking, oh, I can apply it to many other things, it was actually quite hard for us to decide to find a way to map that state action abstractions onto our testing problems. And I'm not sure we got the best one. We got one that works, but we still saw that randomness is still very effective at finding bugs when you have a good generator. Okay, so this brings me to the second thing I wanted to talk about, which is our more recent Codemosa work. So what I've been talking about so far is about test input generation. We were talking about testing this insert function and generating different types of trees to pass as input to this test. So what we were talking about in RLCheck was test input generation. What I'm going to talk about in the second part of the talk is a different automated testing program, which is test suite generation. So where, say we're actually given a whole file or a whole Python module under test, which defines a bunch of functions. We don't want to generate just single inputs. We want to generate whole executable test cases that can essentially exercise this module under test, right? So going from generating single test inputs to generating a set of test cases or a test suite. So that's kind of the shift we're making here. And there's an approach for automatically generating these test suites, which is quite popular in academia, and it's called search-based test suite generation. And I'll give you a real high-level view of it, and then we'll get a concrete example. So essentially, the thing it does is it starts by generating some random test cases for your module under test, say randomly calling some of the functions you defined with random arguments. And it uses those for its initial test suite. And then it's going to mutate those test cases, say by adding new function calls or mutating some of the primitive values. And then it evaluates those test cases on your program under test and checks whether it runs them on the program under test, checks the line and branch coverage and some other things. And if one of your test cases increased the coverage of your program under test, you might add it to your test case population as now your best test cases. And you repeat this until full coverage or some time limit is reached. I'll give you a concrete example of this, and we'll look at a lot more Python code, but let me start by blinding out this part. Essentially, the function we're testing is this bump version function. And what it does is it takes a version string, like of a software system, and increases the version. So here, from 0.00 to 0.01. And it actually is quite a complicated function because it can do different stuff like bump the version at a certain position in this string and add some other things like an alpha, like, oh, it's version 0.10 alpha. So it has a bunch of different functionalities that I've omitted mostly on this slide. What's included here is just the core of that bump version, and then the code for handling that green integer, that position argument. So here, if we were to generate random test case for it, we might get random test cases like this, where essentially the version string they generate is like a random string or none. And when you run these test cases on that program, you'll get very low coverage because those are not valid version strings. So this build version info is going to throw an exception early on, and you're not going to cover any of this program, essentially. So then the classic thing we do here is like, oh, well, we'll create new test cases by mutation, say by mutating that input string somewhat or adding a new function call. But we can keep doing that again and again, and we'll not be able to increase coverage of the file we're testing. So we wouldn't update the population here. So the question we were asked in this project is, what can we do about this? Can we get this search algorithm to get out of its stalls? And that brings us to the idea behind Codemosa. So the idea in Codemosa, right, is that when you find yourself that you've got into such a stall, well, first of all, we'll add a check. We'll see whether the coverage has stalled. So essentially, whether we've gone through n iterations of this mutation without increasing the coverage of the program under test. And in our experiments, we use n equals 25. And so, if the coverage hasn't stalled, if we're making progress with our mutation, we'll go as usual. But if it has stalled, we're going to ask for a hint. And the question is how do we ask for a hint? And as the time we were thinking about this problem, large language models came up. And actually, you might have heard of these because of ChatGPT, which was released last November. It uses reinforcement learning and large language models. You can ask it to do things like generate binary search tree implementation or some tests to put on your slides. But actually, ChatGPT is not what we use in this work. Before ChatGPT, there was this large language model named Codex, which was released in August 2021, and it was released to much fanfare. And you can see these guys, code up some JavaScript game on it. So this Codex large language model is the one that we use in this work. So yeah, so how do we ask for a hint for a test case? we're going to ask one of these large language models. So we'll create a prompt to this large language model to create a test for a function that is not well covered. Then we ask Codex. Codex gives us some, text. We turn that text code into a mutatable format that we can then integrate into our search-based loop. So we evaluate those test cases on the program under test. And if one of those Codex generated test cases increases coverage, we'll add it to the population. And the nice thing about this is that we can get this synergy between the large language model and search. So, right, if the large language model gives us a good suggestion, we'll bring it into our population. Then we're no longer stalled. We might mutate it, and we might actually find that that mutated test case is even better than the one that the large language model gave us. So to show you how this works on the concrete example, say we're again at this case, we're testing this bump version program. Our evolved test cases, as we saw, we could not generate a version string randomly. So we're stalled. So rather than continuing to mutate these for the whole time limit, we're going to go ask Codex for a hint. And we'll ask Codex to create some tests for bump version, and it might create this test, which is actually on a valid version string. And we'll extract that test into this, mutatable test case format. And now when we run it on the program, we actually get huge coverage increases. So because it's actually a valid version string, we actually exercise code in the program under test. So we'll add it back to our test case population. But in this highlighting what I've done, the green lines are totally covered. Those yellow lines are branch statements that aren't only one side of the if statement is covered. So on the next iteration too, we don't need to ask for a hint again, right? Because we just made a big coverage increase. So we'll try to go and mutate these test cases. And, we might mutate the test case to turn the position from 1 to -1 or from 1 to -2687. Pretty simple mutation. We're just mutating integer values. And actually that first mutant will execute this part of the code, and the second one will execute this part, and we'll add both of these tests to our test case population. And just as a spoiler on this benchmark, what we saw is that the classical approach, the search-based software testing only approach, was only able to achieve 18% line and branch coverage of the program under test. Codex only, so if you just asked Codex to generate test cases, actually did much better on this benchmark. It generated 65% coverage. But our approach was able to generate test suites that had on average 92% coverage. And astute summation people in the audience might notice that actually our approach is better than the sum of its parts. So it's really exploiting the synergy that it can cover things that both approaches on their own don't cover consistently. So hopefully I presented this in a somewhat understandable manner. There are some challenges here, like when do you ask for a hint, right? We came up with some ideas for that. How do you ask for a hint? Like what prompt do you use when you talk to the large language model? And how do you handle this potentially arbitrary input from Codex? So in the paper, we did address some of these challenges. We address these challenges in one way, right, by the stall calculation we talked about and backing off when a hint is not helpful. Our prompts are really simple, just looking at the implementation and then a unit test header. And we handle some arbitrary input from Codex by adding some support for new syntax statements that Codex might generate. But this is not these are the solutions we first evaluated, but I think there's a lot of space here to explore different ways to solve these challenges. So yeah, let's get to how our approach works. So we evaluated this approach on 486 files taken from 27 Python programs. We ran each technique 16 times because they're non-deterministic for 10 minutes each. We compared to a search-based software testing only baseline, MOSA, and the Codex only baseline. And in the paper, we do a bunch of evaluation of our design decisions, but here I'm mostly just going to highlight two results for you. So the first is a final coverage comparison. So we look at the code coverage each technique gets at the end of search time. We average it over all runs, and then I'm going to do some statistical significance testing because of that non-determinism in the approaches I mentioned. So on the x-axis, we're going to have the baseline coverage, and on the y-axis, we're going to have our coverage. So first, let's talk about the boring parts of the evaluation. So there are actually a lot of benchmarks on which we don't have a significant difference in coverage over the baseline. So you can see, actually, on many of them, there's exactly the same coverage. So Codex wasn't really able to help out, or Searchbase wasn't really able to help out over the baseline. You can see most of those are aligned on the x equals y line, which means the baseline and our coverage was the same. Okay, so there's some benchmarks on which that happens. There's some benchmarks on which actually the baseline technique gets higher coverage than our approach. It's 11 for the search-based software testing and 4 for Codex only. But on the grand majority of benchmarks, actually, we get significantly higher coverage than either of our baselines. It's hundreds more benchmarks compared to the search-based software testing, and I think over 200 benchmarks we did better than Codex. And essentially, that's all those plus crosses, those pluses above the x equals y line. And what you can kind of see in a high-level trend here, compared to Codex, we were getting a lot more coverage increases, but they're not necessarily of huge magnitude. Whereas compared to the search-based software testing, we got somewhat, we still got many coverage increases, but you can see that, the points are way above the x equals y line, so we get huge coverage increases. And just to give you some common causes for the improvements here, I analyzed the 20 benchmarks with the biggest coverage increases. The most common thing was that Codex was able to generate, special strings like that version string, or say JSON for something that parsed JSON. I haven't really talked about this, but on 7 out of 20 benchmarks, we're testing Python. The search-based thing has difficulty because of not knowing the types of things, whereas Codex can sometimes guess how to construct data correctly without type hints. And on 5 out of 20 benchmark, Codex introduces new syntactical constructs. This is a pretty boring new syntactical construct, the list, but this list operator in Python, it actually iterates over its argument. So that means that you can now actually conduct iteration in your tests, which is not something supported by the search-based software testing. And then the other little point of evaluation I want to leave you with is this question that I had, which that I was wondering, is Codex just copying tests? Would this work? Because Codex was trained on almost all of GitHub. So I think one of our benchmarks, we think it was not on GitHub, but some of the other ones are. So is it just copying tests? Could we get similar results there? And the thing that made me want to investigate this is, I saw this particular Codex generation when I asked it to generate a test for one benchmark. And when I did some automated scraping, we found this test function in another part of the project, which is outside of the prompt we gave Codex. So it sure looks like in this case, Codex knew what this test looked like. And we figured out that we can identify such examples by looking at relative edit distance. So these examples, if you look at their string edit distance, the similarity metric we can derive from that, you get 0.7 similarity, which is quite high. So I actually, did a large scale evaluation of this and looked at, so these are plots of essentially the cumulative percentage of tests that have similarity less than the edit distance on the x-axis. So the last example we saw was edit distances of 0.7, that's about here. But you can see that the grand majority of tests actually have similarity less than 0.4. So it looks like Codex is generating stuff that's somewhat new compared to other tests in the code bases. And the other challenge I want to leave you with here is that we only evaluate the coverage achieved. And of course, when you're going from 18 to 91% coverage, that's hugely important in terms of bug finding power. But in general, people have found that just increased coverage, while it correlates with finding bugs, isn't exactly the same thing. So one thing we might want to see is, can we actually find bugs with these automatically generated test suites? And actually, as we saw, the Codex generations often contain asserts. In this case, actually, the assertions have wrong semantics, but it might be useful to see whether these assertions can help us find bugs automatically in the test suites. Right, so as I said, those ones capture the wrong semantics, but there's essentially what I want to leave you with here is that this is a first pretty promising result, but there's still a lot to evaluate here. So big takeaways from that, right? We saw big coverage increases, big potential from including these large language models. There's a pretty big negative of them, which is that they rely on a closed access API from OpenAI, which is not so nice when a lot of these, random testing you can do on your own. You could write your own random testing on your own. And there's still a bunch of questions to solve here, right? From the bug finding ability to, could we create more complex prompting that could actually better take advantage of these large language models? So that's about all I prepared today. So again, today I mostly talked about these two works, which are looking at the intersection of machine learning and testing in my work. My website's up there, and my email if you have questions that don't get addressed in our Q&A period. But yeah, I'm happy to take any questions about these works or about the field of automated testing more broadly.
Yeah, thank you very much. It was a very nice talk. Thank you very much.